All right, guys. Today we're going to be continuing on with probability. We're going to be talking about independent events today. For Monday's homework, I asked you to finish the notes. So that looked like this. All right. So a couple of you emailed me saying you had trouble filling in the Venn diagram. If you had trouble filling in this Venn diagram, that was probably because you did not write out these numbers out here on the outside. Right, writing those numbers out there are going to help a lot with filling in your Venn diagram. So the way I got the 0.52 was that if 48% of students don't participate in theater, well then 52% have to participate in theater. So that was it. And then once you write in those numbers and you fill in what you can in the Venn diagram like that, right, you can figure out that number and this number. Right, it makes it a lot simpler. So as a two-way table, I thought we do that as a warm-up today. So take a minute and fill this in. All right, so all I did right now is I filled in the given information, right? The 40%, 34.8%, and 48% that don't participate in theater. So if you just fill this in, well, you don't really have enough to fill in the rest. So what you need to know is that the total, right, for any relative frequency two-way table, that is going to add up to 100%. All right, so once you fill in that one, you can fill in the rest using addition and subtraction. So 0.52, 0.348 minus 0.52, what is that equal to? 0.172 maybe? All right, so anyway, I'm gonna pause the video, fill in the rest of the table. All right, so there we go. There's the table filled in. I also converted it to a 1,000 hypothetical two-way table over there. So I just pretended that there were 1,000 total students at Rufus King High School, right, made down 1,000, and then you can just multiply all the values by 1,000. Right, if I ask for 2,000 hypothetical two-way table, just multiply all of these relative frequencies by 2,000 to get the frequency, right, or the hypothetical frequencies in this case. So that is that. Something I should have mentioned in the last lesson, which I didn't do, is you do need to write out let statements. You do need to define your events. So if A equal participates in athletics and T equals participates in theater, right, each using proper notation, right? So what's the probability that a student participates in both theater and athletics? So if you just wrote probability of T and A without writing out these let statements, on an assessment, I would have to take off a point if you did not define what T and A are. So just make sure you're doing that. So the probability that a student participates in theater, that's T, and symbol for and participates in athletics, right, is theater and athletics 0.252. And if you're using the frequency two-way table, right, you could just do 252 divided by 1,000. That's also fine. Or if you want to write this as a percentage, make sure you use the exact percentage whenever possible. So that would be 25.2%, right? All three are equivalent. And by the way, I know we divided by the total here, but you can really do the same thing in the relative frequency table. It's 0.252 divided by 1 is also 0.252. So it doesn't make a difference. What's the probability that a student who is in theater participates in athletics? So we're only looking at students who are in theater. A student who is in theater. So that is a conditional probability statement, right? That is our given. So our given, here's our given symbol, right? Given that they are in theater, what is the probability that they participate in athletics? So, right, we read this as probability of A given T. And if you remember the formula, well, this is the formula, probability of A and T over probability of T. And you definitely need to know that and know how to use it because we will be using this quite a bit. All right, but I want the formula to make sense. So it makes sense when you look at the frequency two-way table. So probability of A and T. So actually, I'm not even using the formula right now. What's the probability that someone is in athletics given that they are in theater? So given that they are in theater, we're looking at these 520 students, right, who are taking theater. And 172 of those 520 students also take athletics. So given that they're in theater, that's going to give us this 520 on the bottom, right? Out of the 520 in theater, 172 are also in athletics. So that's the answer, right? Using this formula, probability of A and T, well, probability that there are in athletics and theater is 0.172 over the probability that they are in theater. Well, what's the probability that someone is in theater? Oh, there's a 52% chance they're in theater. And of course, that is the same thing. That's 172 over 520. So here we go. That's your answer. If you want to use the probability formula for the frequency table, well, the probability that they're in theater is 172 over 1,000, right? And then 520 over 1,000. You get the same exact thing here, right? But hopefully thinking about it makes sense, and hopefully also using the formula makes sense for conditional probability. And yeah, that is that. Oh, I think on the notes yesterday for the key, right, I approximated this as a percentage, right? That is actually not good. You want to keep your answer as exact as possible. So the best way to write this answer is as just this fraction here, 172 over 520. You don't even need to simplify. But if you want, you could make it into a decimal or a percentage. But I'd also tell you to round to something, right? If I just ask, what is the probability? You want to give me the exact probability, so you should only give me this answer, right? Unless you want to give me enough decimal places that it's exact, which I don't even know if you can. Okay. So Larry, find the probability that a student participates in neither theater nor athletics. So if you are in neither theater nor athletics, it means you are not in theater and you are not in athletics. So if you're not in theater, that's the complement of T. And not in athletics, that's the complement of A. And so if you're in neither, that chance is 0.252. Or you can tell me 252 out of 1,000, right? Doesn't matter. All right, so let's take a look at our first example here that deals with independent events. A monk in Shangri-La sits underneath a willow tree and flips a coin. The probability of him flipping heads is 50%, right? As would be true for any other kind of student or any other kind of person. Meanwhile, in quarantine at Great Neck, a student flips a water bottle. The chance of the water bottle standing upright after flipping is 20%. So what is the probability of water bottle landing on its side? So I don't want to write that out every time. So you have to write a let statement. So I'm going to let U equal water bottle lands upright. And for the heads, I'll just say let H equal coin lands heads. All right, so what is the chance that a water bottle lands on its side? Well, that would be U complement, right? Not standing upright. So I know there is a fringe case where water bottle lands like this, upside down, but I guess we can consider that upright, maybe, or I'm just going to ignore that, small chance. But anyway, probability of the water bottle landing on its side would be the complement of it landing upright, which would be 0.8. So there's an 80% chance of the water bottle landing on its side. Chance of the monk getting tails, probability of, you can't say T because we haven't defined T. If you want to define T up above, that is fine. Or we can also write this as the complement of heads. And of course, that's also 50%. All right, so let's think about these two events. Does the outcome of one event affect the other event? Do you think they are independent or dependent events? So does the monk getting a head or a tails in Shangri-La, many hundreds of miles away, affect our probability of when we flip this water bottle that it lands upright or on its side? And of course, those two events do not affect each other, right? The outcome of one event does not affect the other. The outcome of one event does not affect the other. And we call events like this independent events, right? Because if you're independent, right, you stand by yourself, right? Whereas two events that do affect each other, they're going to be called dependent events. So let's take a look at B. Given that the monk gets a heads, what is the probability of the water bottle standing upright after flipping? Write this using conditional probability. So what's the probability of upright given that the monk gets a heads? Well, we just talked about how these two events don't affect each other. So given that this monk got a heads, well, does that affect the probability of us flipping the water bottle and having it stand upright? And the answer is, of course it doesn't. It doesn't matter whether the monk got a tails or a heads or 100 tails in a row prior to us flipping this water bottle, right? The probability of it being upright is still going to be 20% because that is our skill level at flipping a water bottle. It stands upright 20% of the time. So it doesn't matter what the monk did in Shangri-La or what was the outcome of his experiment, right? But whatever happens, our chance is still 20% because they are independent events. Right? And so lastly, what is the probability of the monk getting heads and the flip bottle standing upright? Well, the chance of the monk getting heads is a half, right? And the chance of the water bottle standing upright is a fifth, or 20%. So the chance of both happening is a tenth. And we are allowed to multiply these probabilities together because they are independent, because they don't affect each other, right? So yeah, so we'll leave it like that. We'll take some notes in a little bit, but this is only true. You're only allowed to multiply individual probabilities to get the combined probability when those individual probabilities are independent of one another, all right? So similar example over here, imagine two events, spinning the spinner shown to the right and rolling a fair six-sided die. I'll just fill this in real quick. If you roll a die, you have a 1 out of 6 chance of getting a 6. If you spin a spinner, you have a 1 out of 4 chance of getting a 3, right? Because there are 4 equally likely outcomes, and we have 1 that satisfies our condition. So therefore, if I roll a 6 and then spin a 3, what is the chance of that happening? Well, I would say that these two events are independent, yes, because when you roll the die and then you spin the spinner, one outcome does not affect the other outcome. So these are independent events. So again, we can just multiply the two probabilities. So chance of rolling a 6 is 1 out of 6. The chance of spinning a 3 is 1 out of 4. The combined chance of both happening is 1 out of 24. Right, this should also make sense if I draw a sample space, like a tree diagram sample space. I'll do that real quick. So these are all the possible outcomes when I roll a die. And then if I roll a 1, well, then I have 4 additional possible outcomes once I spin the spinner. I can roll a 1 and then spin a 1. I can roll a 1, then spin a 2, roll a 1, spin a 3, roll a 1, spin a 4, right? And same thing for all these. If you count all the branches here, there are 24 possible outcomes when I roll a die and spin a spinner, only one of which is rolling a 6 and spinning a 3, satisfies my desired conditions. So that is 1 out of 24 outcomes, which is exactly what we have here, 1 out of 24. But we're never going to do it that way, right? Just showing you that it's the same whether you do it with sample spaces or just multiplying probabilities. What's the probability of rolling a 6 given that you spin a 3? Well, given that I spin a 3, doesn't affect my chance of rolling a 6. I could have spun a 4, and I will still have a 1 out of 6 chance of rolling a 6. Right? If I spun a 3, or sorry, if I rolled a 6, given that I rolled a 6, what's the chance of spinning a 3? Still 1 out of 4. And because one event did not affect the other event, we can say that these events are independent, right? So up above here, that is how things behave when they are independent, right? When events are dependent, it gets a little bit trickier, and there's more things we need to consider, right? So for example, 2 here, we're not going to calculate anything. We're just going to think about it. But given that the probability of it raining on a spring day in New York is 20%, what is the probability that Lisa goes outside with an umbrella? I'm sorry, if the probability that Lisa goes outside with an umbrella is 15% on a given day, make an estimate of the probability that it is raining and that Lisa goes outside with an umbrella on a given day. Well, if we were treating it like the ones above, well, first of all, sorry, let me define my events. So let R equal rains on a spring day in New York. I'm just going to say R equals rains, and let U equal Lisa goes out with umbrella. All right, so we want to make an estimate of the probability that it both rains, probability that it rains, and that Lisa goes outside with an umbrella. Well, when we did these probabilities before, for example, over here, right, we just multiplied the two individual probabilities. And we said that is allowed when they are independent. So if these events were independent, we would be able to just do the probability that it rains, 20%, 0.2, times the probability that she goes outside with an umbrella, and that would be 3%. Well, let's think, does that make sense? Would that be a good estimate? Make an estimate of the probability that it is both raining and that Lisa goes outside with an umbrella. Well, if it's raining, then it's probably a very good chance that she goes outside with an umbrella, because you take an umbrella outside with you when it's raining. So these events are clearly not independent. These are dependent events, right? Because the fact that it rains affects whether or not you go outside with an umbrella. So hopefully you can see that the probability would be a lot more than 3%. So take a second, try to make a good guess about what the combined probability might be. And so for myself, I might guess something close to 15%, right? Probability of R and U, it's going to be, or should be, close to 15%. Right, but it also has to be less than 15% because there's only a 15% chance she goes out with an umbrella on a particular day. So it should be less than 15%, but it should be close to 15% because pretty much every time it rains, she's going to be going out with her umbrella. Does that make sense? I hope that makes sense. It's kind of hard. I think a lot of you have questions right now. But the probability that it rains and that she takes an umbrella out should be close to 15%. Because if it is raining 20% of the time, well, on those days that it rains, she is very, very likely to be going out with an umbrella. So the fact that this isn't also 20%, if this were also 20%, it would probably mean that every time it rains, Lisa goes out every single day and she always carries an umbrella, right? So every time it rains, she carries an umbrella. So the fact that this is less than 15% means that she probably doesn't go out every single day. But if it were raining and she goes out, she's probably going to carry an umbrella. So the probability of both should be close to 15%, all right? So would it make sense to multiply the two probabilities together like we did in the previous two examples? No, right? And that's because the events aren't independent. And also, we just think about it logically, right? The probability of it raining and that she carries an umbrella, right? That is not going to equal 3%, right? Because if it's a 20% chance of it raining and she's going out on that day, then she's probably going to be carrying an umbrella. So it's going to be much more than 3%. So I have another example to illustrate events that are dependent below, if that didn't make too much sense. So let's take a look at example number 3. A person randomly selected in Great Neck South High School after 6 p.m. A person is randomly selected, so the chance that, I'm sorry, give me a second, I'm going to pause this and restart. All right, so the probability that the person that was randomly selected is a teacher is 20%. The probability that the person wears a tie is 10%, and the probability that the person is both a teacher and wearing a tie is 9%. So let's define our events first. So I'm going to say let T equal the fact that the person is a teacher, right? Equals person is a teacher. And I'll do wearing tie as WT. Person is wearing a tie. So let's take a look at A. Do you think the events of being a teacher and wearing a tie are independent events? Well, for me personally, I see a lot more teachers wearing ties than just general population of people wearing ties. So I would say, no, they're probably not independent, right? They are likely dependent because they wear ties more often. At least male teachers do. But they wear ties more often than the general school population. So let's think, does one event affect the other? If the person is a teacher, well, doesn't that make it more likely that person wears a tie, right? So these events do have an effect on one another, so therefore they are not independent. They are dependent on each other. And the same is true the other way around. If a person is wearing a tie, doesn't it make it more likely that they're a teacher, right? Or they could be an administrator of some sort? But either way, it's more likely that they're a teacher than if you just pick a random person and they're not wearing a tie. So how can we tell this using the given probabilities? Well, if they were independent, remember, we can just multiply the probabilities together and we would get the combined probability. So if I did 20%, times 10%, I would get 2%. And I did not get 2% because the probability that a person is both a teacher and wearing a tie is 9%. So because the probability of tie and, sorry, not tie, probability of the person being a teacher and wearing a tie did not equal the probability of them being a teacher times the probability of them wearing a tie. Right? These two probabilities did not equal each other. And that's called the product test for independence. That is not our main focus for today, but I just wanted to show you briefly over here. Right? So the probability of teacher and wearing a tie was 0.9%. Sorry, not 0.9, 9%, which is 0.09. I don't know what I'm saying. All right, so 0.09 did not equal 0.2 times 0.1. Right, 0.09 did not equal 0.02. So if they were independent, there would be a 2% chance of both events happening. But in actuality, the percentage is 9%. So write out and evaluate two conditional probabilities based on the information above. So I'm going to say, what is the probability that the person is a teacher given that they wear a tie? So again, remember when they were independent, that these conditional probabilities, well, this did not affect the probability of spinning a 3. So going back to this spinner rolling die example, the probability of spinning a 3, given that I rolled a 6, that was still equal to the probability of spinning a 3. Because whatever happened with that rolling a die did not affect the probability of spinning a 3 on the spinner. So this condition had no effect. But in this example, with the teachers, we're saying these events are not independent. So the fact that they wear a tie is going to have an effect on this probability of them being a teacher. So let's use the formula. The probability of teacher given that they are wearing a tie is going to be the probability of teacher and wearing a tie over the probability of them wearing a tie. All right, so it's kind of looking at, if I just ignore these p's for a second, it's kind of looking at, we're taking a look at the total population of people wearing a tie, and then how many people out of that population are also teachers. So we have to look at those wearing a tie and being a teacher. So that's how this formula works. So probability of teacher and wearing a tie was 0.09. And there was a 10% chance that the person was wearing a tie. So if you calculate this, this is 90%. That's 0.9. So hopefully that makes sense, because given that the person is wearing a tie, there's a 90% chance that person is a teacher, right? The other 10% probably could be the vice principal or the principal, and that's pretty much it. Or some office staff, someone else that might wear a tie, but pretty much in a school population, only teachers wear ties. So if that person's wearing a tie, there's a 90% chance that person is a teacher. And let's take a look at the other way around. What's the chance that the person is wearing a tie given that they are a teacher? Well, what's the chance of someone wearing a tie and being a teacher? That's going to be the same on top. So let me actually write it out. Probability of wearing a tie and being a teacher over the probability that they are a teacher. So that's 0.09 over, what's the chance that they are a teacher? It was 20%. That's 0.2. And that's equal to 45%, I believe. Yes. All right, so there's a 45%. Let me double check that, because I know it is, but I don't know. I feel like double checking for whatever reason. 0.09 divided by 0.2. All right. That is 45%. So given that you're wearing a tie, given that you are a teacher, there's a 45% chance that you also wear a tie. And that also makes sense because most male teachers wear a tie. Maybe not most, but I think most. Most male teachers wear a tie, so let's say half the teachers are male, and that's why it's pretty close to 50%. So given that you're wearing given that you are a teacher, right, there's a 45% chance you're also wearing a tie. So as we can see, because these are dependent, right, the probability of wearing a tie again was just 20%. Right, was it 20%? Sorry, 10%. Right, and the probability of being a teacher was 20%. But once we add in this condition, this probability skyrocketed way up, right? And now it went to 90% after I included that condition. So this obviously had a huge impact on whether or not the person was a teacher, right? Same thing here. Given that the person was a teacher, had a huge impact on the probability of whether or not they wore a tie, right? 45% compared to just 10% if we do not include the given. So for conditional probabilities, if the events are dependent or not independent, then it's going to have an influence on this probability, right? So let's write down everything we figured out, hopefully, in this nice box over here. So if two events are independent, then the occurrence of one does not change the probability of the other occurring. Right, and that was the example with the monk and the water bottle, or a die and a spinner, right? Whatever happens with one thing doesn't affect the other. So if events are independent, then the probability of them both occurring is the product of the probabilities of each occurring. Right, and example of that is right here. Right, if they're independent, you can just multiply out the two individual probabilities, and you'll have the probability of both occurring. Whereas if they are if they are dependent, right? We saw that it wasn't true for the raining example. Also, with the teacher example, you can't just do 20% times 10% and get the probability of both occurring, right? So that's our summary in words. Let's write it out with our notation. Let's say we have two events, A and B. Probability of A and B is going to equal the probability of A times the probability of B, if the two events are independent, right? This is only true if two events are independent. So if two events are independent, right? If events are independent, then, so I just wrote it out using probability notation, and the probability of A and B equals probability of A times probability of B, right? If they are dependent, obviously that is not true, right? Similarly, we saw with conditional probabilities that the probability of A given B was equal to the probability of A if they are independent, right? Because then we're saying that this outcome of B happening has no effect on the probability of A, right? Just like when you rolled a 6 on the die and then you spun the spinner, well, it didn't matter about this outcome, right? Probability of A was still probability of A, even if B happened previously. And then the same thing for the other way around. Probability of B given A is also going to equal probability of B. Right, so this is true if the events are independent, and therefore, if events are dependent, then none of that is true, right? Because then one event is going to affect the other event. Then you can't just multiply the probabilities together. And when you look at conditional probabilities, that condition will affect the probability of the other event happening. So we can just put does not equal symbols for each one of these. And that is pretty much what you need to know for independent probabilities, at least for right now. But hopefully it made sense how we got these conclusions, right, from the examples we did. It can be a little tricky or hard to think about, but I'm hoping that these do make sense, because I don't want you just memorizing formulas, right? But if you have any questions, let me know. But this is our summary from our lesson so far. So let's answer some questions. So number 4. And by the way, we're going to be doing more of this tomorrow, right? We're going to call that the product test for independence. So for today, I want to focus in on using these facts, right? That if events are independent, then their conditional probabilities are going to equal just the probability, right, without the condition, because that condition doesn't really affect the probability, again, if the events are independent. So are the events, the student is female and the student is left-handed, independent? Well, if they are independent, then the probability that the person is female, given that they're left-handed, is going to equal the probability that they're female. Right? In other words, again, This condition of being left-handed has no effect on the probability of that person being female. Right? So I'm going to write out every day. If independent, then this is going to be true. Right? Or we can do it the other way around. It does not matter which way you set it up. Right? If they're independent, both of these are going to be true. All right, so let's just do one. So let's do this one. And we're really seeing if this is true, so I'm going to put a question mark. Same thing for this. So what's the probability that the person is female given that they're left-handed? So given that they're left-handed, there's 3 people that are left-handed and 3 of them are female. So the chance that they're female given that they're left-handed is 3 out of 4. And what's the probability that a student is female? Well, 21 out of 28. And 0.75 equals 0.75. So yes, this checks out. The events are independent. Right? Being a female and being left-handed is independent. The events are independent because the probability of being female given that you are left-handed was equal to the probability of being female. So the fact that you had left-handed had nothing to do with whether or not you were a female. Right? Or the events the student is male and the student is right-handed, independent. So we're going to do the same test. Probability of male given that they're left-handed, does that equal the probability of them being male? And so the chance that you're male is 1 out of 4. Given that you're left-handed, right? So given that you're left-handed, 4 of them are left-handed, chance that you're a male is 1 out of 4. And chance that you're a male overall, there are 7 males out of 28. And so yes, they are independent. 0.25 here equals 0.25. All right, let's take a look at one more example here, number 4. Two-way frequency table shows the proportions of the population that had their given hair color and eye combinations. Use this table to answer the following. So show that the events of having green eyes and red hair are dependent. So I know I said we're going to be using the product test tomorrow, but let's use the product test for this one. We'll look at a sneak peek. So first of all, I'm going to say let G equal having green eyes, and let R equal having red hair. So if they were independent, then we can say the probability of having green eyes and red hair is just the product of the 2 individual probabilities. So because they are dependent, we want to show they're dependent, we want to show that these are not equal, right? So what's the probability of having green eyes and red hair? 0.15, 15%. And let's show that that is not equal to the probability of having green eyes, which was 25%. 0.25 times the probability of having red hair. Chance of having red hair is 0.18. I put those in parentheses. And what is 0.18 divided by 4 times 0.045? Right, so we can say because this was not true, the events are dependent. Also want to show it using conditional probabilities. So what's the probability of having green hair given that you have, sorry, green eyes, green hair. What's the probability of having green eyes given that you have red hair? Does that equal the probability of having just green eyes? right? And of course, we know already that they're not going to be equal because we said they're dependent. So having red hair will affect this probability of having green eyes. But let's take a look. What's the probability of having green eyes given red hair? So given red hair, out of this 18% of the population, how many have green eyes? 0.15. And let me calculate what that is equal to first. 15 over 18, that's 0.83 repeating. All right, we get 0.83 repeating here. Let's show that does not equal the probability of having green eyes, which is 25%. All right, so therefore these are dependent, right? I don't know about you, but red hair and green eyes, they tend to go together. So this is saying, if you have red hair, you have an 83% chance of also having green eyes. And that, of course, is not equal to the chance of just having green eyes, which is 25%. So these affect each other, right? These probabilities are not equal. Therefore, they are dependent. All right, so I'll let you guys finish up 4B and 5, because I think this lesson is going pretty long. But I would like you to use these facts for independence to prove whether they are dependent or independent. Yeah, so give that a shot. I will post up these problems as part of the notes. Yeah, I'll post a PDF of the notes with these two completed. Number 5, you have to think a little bit more about this one. This is a good thinking problem, so try number 5. And that's going to be it. This is a tricky concept for some people. So if you have any questions, let me know. But we will continue with more independence tomorrow. So that's going to be it. See you guys later. Take care. Bye-bye.